So in this video, we are going to calculate the moment of inertia, this time of a disk, about first an axis that passes through the center of the disk, and secondly about an axis that passes through a diameter of the disk. So the idea, as usual, is to be able to select an elementary mass that has the same symmetry as the object, as the mass distribution we require to calculate the moment of inertia. So in this case, you have the disk. So if you want to select an element that has the same symmetry as the disk, of course it's going to be a ring. So we define a ring. We choose a ring here that has a radius of small r. Already the disk in black has a mass of m and a radius capital R. Okay, maybe we put it like that. This is the radius of the disk. And then the ring has a radius of small r, a mass of dm, and it has a thickness of dr. So it's going to have a very small thickness that we can call dr. Let me represent it here. So this thickness, that and that, is dr. Okay. So since the disk has a uniformly distributed area, a uniform mass distribution, we can call that mass distribution, let's say, sigma. So sigma is going to be the mass of the disk over its area, which is just pi radius squared. Okay, and this of course has to be equal to dm, the mass of the element, divided by its area. So to calculate the area of this ring, we just take the circumference. The circumference of the ring is just 2 pi r, and then we multiply times the thickness, okay, this little thickness of the ring, which is dr. So 2 pi r dr is the area of the ring, and this is the mass distribution. This means that the mass of our element, of our ring, is going to be, we can simplify that, so that's going to be m on pi r squared times 2 pi r dr. Okay, we can simplify that further. So pi cancels pi, and we are left with m on r squared times r dr. Okay, times 2r, so I'm going to put the 2 here. All right. Then the moment of inertia of our disk, so let's say I of disk, is going to be the integral, okay, of the moment of inertia of the element, the tiny element, which in this case is the ring. So that's going to be the mass of the ring, which is dm, times the square of the distance to the center of rotation. So that's r squared. We integrate over the entire mass of the ring. So we get I of disk as the integral of r squared. We replace dm, that's 2m divided by r squared times r dr. Okay, in this case, small r has to range from 0 to capital R because we need to generate the entire, the whole area of the disk. So the ring has to sweep from values of R going from 0 to capital R. Okay, you can see that. So imagine you have this and it just grows like that. All right. Then this integral becomes that integral from 0 to R. Then we have here 2m over capital R squared, which is just a constant, times r cubed, then dr. So if we integrate that, we are going to have I of disk. We are just integrating r cubed, so we are going to have 2m over r squared, which is a constant, times r 4 on 4. And then we apply the boundaries of integration. So that gives us 2m divided by r squared times r to the power 4 on 4. And if we simplify this, you can see that we're going to have an r squared that will cancel with this r4. So at the end, we're going to have I of disk as m r squared over 2. And this is the moment of inertia of a disk about an axis that passes through the center and that's perpendicular to the plane of the disk. So we can go further and calculate now the moment of inertia about an axis that passes through the diameter of the disk. Just as we did in the previous set of videos, we need to apply here the perpendicular axis theorem. So perpendicular axis theorem, which in this case, just as was the case of the ring, tells us that Iz is going to be Ix plus Iy. So X is an axis that passes along a diameter as well as Y. So X and Y are just diameters, if you want, of this disk. Then Iz is related to Ix and Iy as the sum of the two. Okay? Remember that this only holds if the two axes we consider are perpendicular, and that this pair of axes is itself perpendicular to the third axis. So here we need 3 perpendicular axes. So that's important to take note of. All right. Again, due to the symmetry of the disk, Ix is equal to Iy, which means that Iz is going to be 2Ix or 2Iy. But this implies that Ix would be equals to Iy, which is equals to Iz over 2, which is just this expression, mr squared on 4. So this is the expression for the moment of inertia about an axis passing through a diameter. So that's mr squared on 4. Okay, let me put that in red. All right. So hope all that's clear, and see you in the next part of this video series.